Okay, so it's a great pleasure to have Shane Kelly as our next speaker, and he will tell us about motives with modulus over a general base. So thank you.
Yeah, well, it's a great pleasure to talk at such a conference. So thank you very much for the invitation. I'm very happy to be a part of this. So my talk is about some work that I've done with Hiroyasu Miyazaki on motives with modulus over a general base. But this is just, one kind of chapter or section in a long research program that involved many people, which I'll mention along the way. So the question that I thought I would start with is, well, what is a motive with modulus? Which is a very common question when you see this term. Well, I say I want to start with the question, what is a motive with modulus? But I'm actually going to start with the question, what is a motive? Because there's many different answers to this question. There's many ways of approaching this subject. So some possible answers about what a motive is so it's a universal cohomology group, or it can be a symbol, so a pair with some x and some pi. Or another possible answer is it's a constellation of vector spaces. Or another possible answer is that it's a homotopy type. And there's many more answers that are possible, like a representation of an appropriate Galois group, which, and yeah, so I'm not going to talk about those kinds of things. I'll just go through this small collection of possible answers. Okay, so the first one, a motive is a universal cohomology group. So this is somehow philosophically a starting point for the theory from maybe like the 1960s, I think, where so in topology there's one cohomology theory, singular cohomology, where all other cohomology theories kind of come from singular cohomology. All the information is contained in it. So there's like this universal cohomology theory which gives rise to all of the other ones. And so the behavior of all the various other cohomology theories is governed by the behavior of singular cohomology. And in the 60s, there was this these various cohomology theories for smooth projective varieties floating around, which all had very, very similar behaviors. So this is smooth projective varieties over a base field K. So if your base field is a subfield of the complex numbers, then you can take your smooth projective variety, consider it as a complex manifold, and look at its underlying topological space and just take its Betti cohomology. Or there's also a de-Rham cohomology. And so when these two are very closely related to each other, and using both of them, you can build a Hodge structure. So this Betti de-Rham cohomology takes a smooth projective variety, and from it you can construct a Hodge structure, which is a vector space. It's depending on your what you're doing, it's a free abelian group with a filtration and another filtration on its complexification, which you don't need to be aware of. I'm not going to say, this will not, Hodge structures won't appear anymore. But there's these forgetful functors to rational vector spaces or K vector spaces or C vector spaces. So we have this functor from smooth projective varieties, which lands in various vector spaces. And if we like, we can, but these vector spaces are canonically equipped with some extra structure, which contains more information. Okay, so if you choose a prime different from the characteristic of the base field, then you can look at the L-adic cohomology, the étale cohomology with QL coefficients. And so this takes a smooth projective variety to a QL vector space. So this is the L-adic numbers. And these come canonically equipped with an action of the absolute Galois group of the base field. So again, we have these vector spaces, but they have this extra structure, which will contain more information about the original smooth projective variety. And there's also crystalline cohomology, which I don't really know much about. So this lands in the width. So this is these are the width vectors of the base field, and then you invert P to get to end up with a characteristic 0 field. And again, the Frobenius automorphism will act on these vector spaces, and such an action gives you something called an F isocrystal. Okay, so we have at least these, we have these various cohomology theories, and they all have very similar behavior. And you could ask if the situation is similar to the situation in topology. Is there some kind of more universal cohomology theory through which this functor will factor? So this is one way of thinking about what a motive should be. It's this universal, this category with this functor from smooth projective varieties through which all of these cohomology theories factor, and which will have properties that explain the commonalities of these three or of these other theories. So some remarks is that, okay, so here's our smooth projective variety getting taken to our motive. So this is just some symbol now, some MX, some object in this category, which a priori may or may not exist, that we don't really know much about it, other than that it should satisfy various properties that we want to study. So it should have, this object here should have all the information about all of these other cohomology theories, these cohomology vector spaces. Okay, so yeah, some kind of slippery point, I think, about this point of view is that, so I didn't say what cohomology group, I didn't define what a cohomology group is. So I kind of insisted that it has source smooth projective varieties, but I didn't say anything more than that. And so, of course, if you're asking for something universal with respect to what? With respect to what properties? So depending on the paper, yeah, so you would get different categories depending on what properties you impose. And depending on the paper, this category here could be asked to be Q-linear or semi-simple, or, I mean, these are very common appearing choices, abelian, monoidal. And the third point on this page is that classically, this category is pseudo-abelian. So this means that if you have an idempotent endomorphism of any object, then this will split your object into two direct summands, the image and the kernel of this idempotent. And it's generated by direct summands of, so these images, these MX, which we're thinking of as cohomology. So this is to be thought of as a cohomology of X. Okay, so this leads us to the second answer, is a symbol. So let's go back a bit to whenever you learned about tensor product. So if you have two vector spaces, then the tensor product is defined by a universal property. It's the universal vector space such that various maps will factor through. And this is an abstract definition, and this object may or may not exist. The way that this universal vector space is constructed often is by considering the set of symbols, V tensor W. So V is some element of V, W is some element of W. And then you quotient out by various relations which you would like this universal object to satisfy. So this is, I think, a very useful way of thinking about the various categories of motives that are floating around. Is that, I mean, they're almost all of this form in some sense, where you have some collection of generators which you impose conditions on. So on this page, I said that, so this is generated by direct summands of cohomology of smooth projective varieties. So that's what this symbol. So this is a very, I found a very clear article by Scholl called Classical Motives, which explains, which develops this classical 1960s theory of pure motives very clearly. And so the starting point is the starting point to building this category is the objects are just a pair consisting of a smooth projective variety and an idempotent endomorphism. So some morphism which satisfies, whose composition with itself is not the identity, is pi. And so this is just a symbol, which should be interpreted as the image of, so if we're thinking of this as a cohomology, or we're thinking of mx as a cohomology group, and then adding pi means that we're specifically thinking of the part of the cohomology cut out by pi. So then there's the relations come from the Hom groups, which is often the case in category theory. So when you're doing things like taking quotients of sets under a group by some action, if you, instead of saying that this element is equal to this element, you just put an isomorphism between them. Okay, so on this page, I give a more detailed description of these Chow motives, which is not really so important for my talk, but it's probably going to, well, it's definitely going to appear in Jens's talk, and it's something good to have seen at some point anyway, I think. So here's our definition of the Hom groups in our category of motives. So we have two smooth projective varieties and two idempotent endomorphisms. So the morphisms between these two smooth projective varieties are going to be elements of the Chow group of the product of codimension, the dimension of y, or dimension, the dimension of x. So the idea is if we have just some morphism of varieties from x to y, we can take its graph, and this will give us a cycle, which we can think of as an element of this group. But we want more general, instead of just allowing graphs of morphisms, we want more general objects. So we allow all cycles, and then we quotient by some appropriate equivalence relation. And of course, we want to take these idempotents into account. So instead of taking so if these are the identities, then we take the whole group, but otherwise we take the image of the induced map, the map induced by these two idempotents. So now we have a category. Composition, I don't say anything about, because Jens is going to explain this in his talk, as far as I know. Okay, so then we had this, what about these purple arrows? So now we've got this map here sends X to the pair X identity. And if we have a cohomology theory, where is it? We have a cohomology theory. So this is just some H with a theory of cycle classes. So some nice collection of maps that go from Chow D to H2D. Then the realization functor sends this pair X pi to the part of the cohomology cut out by the idempotent. So the image of this induced morphism. And given a cycle, so given an element of this Chow group, we pull back from the cohomology of X to the cohomology of the product. We take the intersection with the, so we take the, we're going to ask that our cohomology theories have some products defined on them. And we take the product with this, the class of our cycle, and then project down to Y. So the existence of such morphisms are built into the definition of cohomology theory in this setting. Okay, so a footnote to the footnote is that there's, so in general, there's this kind of a, I mean, I don't want to say there's two flavors of motives because there's many different kinds of flavors, but whatever motives you're considering, there's usually an effective version and a non-effective version. And this one that I'm always going to be working with the effective version, but I want to say so that so that Jens can use it, I'll say something about the non-effective version. So another thing that we can ask of our category of motives is that it's rigid. So none of my categories are going to be rigid, but it's a property that you do want. And all of the categories that will appear in my talk can be made rigid. So rigid means that given some motive, given some object in your category, there exists another object such that you have this kind of isomorphism for every pair of objects, M1 and M2. So tensor with M is a left adjoint, and it has a right adjoint, which is also of the form tensor with some object. So this definition here can be made rigid by formally adjoining negative weights in some sense, in a very concrete sense. And one way that, well, the way that this happens in Tony Scholl's article, Classical Motives, is instead of just working with pairs, you also add an integer. And then this shifts the morphisms. So instead of working with cycles of degree D, now we're looking at cycles of degree D plus N minus M. So this is this N and this M. And yeah, so conceptually how you should think about this is, so the motive of some smooth projective variety will be the triple X identity 0. So there's no change in weight. And there's no, so the idempotent that you're dealing with is just the identity. And then there's this other object, which I'll come to in a minute. And if you tensor your mx with L n minus n times, then this is what this n represents. So L is it's the part of the cohomology of the projective line, which doesn't come from the base. So for any smooth projective variety with a rational point, projecting to that point is an idempotent, which will cut out the H0, or the part of the cohomology coming from the base. And then the complementary idempotent to that is the identity minus this projection. So in the case of P1, The cohomology has there's an H0 and an H2. And this projection to the rational point will cut out this H0 part, which is the same as the cohomology of the base field. And this L is the other part. So if you're just dealing with cohomology as vector spaces, then these are going to be the same. It's just a one-dimensional vector space. But if your cohomology vector spaces are these kind of enhanced vector spaces, so you have a Hodge structure or a Galois action or something like that, then this H2 is going to be different from this one. So if you're looking at L-adic cohomology, then you get a QL, one-dimensional QL vector space equipped with an action of the Galois group, which comes from the action on the roots of unity of the base field. And if you're doing Betty-Durham and using Hodge structures, then you get this Hodge structure, which is sometimes written 2 pi I z. And a global disclaimer is that I almost always get all the indices wrong. So there's probably some minuses on this page which are missing, or some minuses which should be pluses, or yeah. But modulo that, I think everything should be okay. All right, answer 3. So this page has a lot of stuff on it, but I mean, I don't want to read all of this. It's really just conceptual. Like I want to put this picture in your head. So the idea, we have this universal picture, and so you might ask, can I think of objects in this category just as the collection of all of the vector spaces they give rise to? So can I think of a motive just as a big collection of vector spaces, maybe with some extra structure? And Deligne says yes. So this is a definition he makes in a very important paper, Le groupe fondamental de la droite projective moins 3 points. This is definition 1.11. And so he defines a motive as this big tuple of information with these 10 objects, which you can look up and read in this article if you want. But I'll just summarize saying that you have a bunch of vector spaces, which will, I mean, which will come from, given a smooth projective variety, which will come from the various cohomology theories. In addition to these vector spaces, you have various comparison isomorphisms between the various vector spaces. So if you tensor Betty cohomology with C, you get the same as there's a canonical isomorphism to Durham tensor with C. There's a relationship between the Betty cohomology and the L-adic cohomologies, and between the crystalline and the Durham cohomology. And then there's various other structures on these vector spaces. And that's a motive over Q in this article, in this article of Deligne. Okay, so there's a lot of information on that page, but you can, this is the point. This is the picture I want you to have, or maybe this picture.
Shane, we don't see any picture there.
Oh, really?
Or, oh, it's very dark.
The picture of a night sky with a constellation drawn on top of the stars. So it's a photograph of a night sky full of stars.
Il est 17 heures.
And then there's various lines joining big stars. So, I mean, the stars are supposed to be vector spaces, and the lines are supposed to be various isomorphisms between them, if you want. And then, I don't know, maybe the stars have little planets going around them, which is the filtrations and the Galois actions and stuff.
Oh, yeah. Okay. It's hardly visible, but okay, yeah. Good.
It's from Wikipedia. I can. Yeah, I don't want to look up that. I don't think it's so important that I find a URL. Okay, so now this is for my description of motives with modulus. I think this is the most important answer. It's a homotopy type. So this is the post-Voevodsky kind of answer. So from the 1990s. So the homotopy category of topological spaces, you build this by taking the category of topological spaces, and then you formally invert these morphisms. So you have the unit interval inside the real line, and you formally invert this morphism, its projection of the various spaces cross with this unit interval to X. And this has the effect that it identifies morphisms which are homotopic to each other, and it identifies spaces which are homotopic to each other. So yeah, one of the kind of paradigm shifting ideas, I guess, that came out of Voevodsky was that you can, not that you can, I'm sure, yeah, so Morel also, this is also due to Morel. Maybe not that you can do this, but that, that he did this and also developed this like big framework of machinery around it, which meant that you could actually like prove a lot of nice things using it. Okay, so this is a definition of Voevodsky's category of motives with rational coefficients. So I don't like talking about, yeah, so strictly speaking, this would be usually denoted dA, which is something which appears in a lot of Joseph Ayoub's work. But I don't like talking about correspondences or cycles in talks because I find it too technical and not really, I don't think it's I don't like doing it, so I'm not going to do it. So if we use rational coefficients, we can ignore, I don't have to do it. So one way of defining this category is you start with smooth varieties over your base field. You take the étale topology on this category of smooth varieties. So they're not projective anymore, just smooth, which was one big advance of the theory. So then you take sheaves of Q vector spaces. So étale sheaves of Q vector spaces on smooth varieties. You take its derived category. So this is a triangulated category. And then you have these canonical, so you have these morphisms from a smooth projective variety across A1, the projection just to the base, using Yoneda. So any smooth variety you can think of as a pre-sheaf. And then you can take the free pre-sheaf of vector spaces generated by that pre-sheaf of sets. The étale topology is subcanonical, so every X will give rise to a sheaf, and therefore you can think of it as a complex concentrated in degree 0. So you get an object in this derived category. Maybe I should write that. So X is, so it's complex concentrated in degree 0 of Q, so the free vector space generated by HOM into X. All right, that, yeah, okay. I guess that's not legible, but I don't want to spend any more time on that. And then you take the Verdier quotient of this triangulated category by the thick triangulated subcategory generated by these, the cones of these morphisms. So you formally invert this morphism. And I should point out that in this definition, you don't need to use the unit interval. You can use all of R and you get the same category because, you can use any contractible space and with, with two chosen points and you get the same category. So this is very much modeled on this, this kind of thing. So this is Voevodsky's category of motives. So some remarks about this, how you can think about this construction. So pre-sheaves, the passage from a category to its category of pre-sheaves literally is just freely adjoining all colimits. So this is a mathematically rigorous statement. So there's this way of going backwards and forwards between a pre-sheaf and a diagram. So the reason this occurs is if you want to use homotopy style arguments, there's a lot of colimits which appear all of the time, which you would like to do, and category of smooth varieties has very, very few colimits. So you add them, you formally add them. So this is a very harmless kind of procedure. The relations that we impose, so these are our generators. Our generators are smooth varieties. And the relations that we're imposing are Q-linearity, étale descent, and A1 invariance. We're requiring that this affine line can be equivalent to the base. And something which is kind of amazing, and I mean, it's the consequence of many big, difficult theorems stacked on top of each other, is that with just these three properties, from this, you get a projective bundle formula, a smooth blow-up formula, Gisson triangles, and you can prove that, and this is, I mean, there's a number of very big theorems inside here, that in this category here, the Homs calculate higher Chow groups. So here's the theorem, or the statement, is that if you have some smooth variety X, some smooth projective variety Y, because I don't want to get into compact support, and D is the dimension of Y, then morphisms from MX towards MY. So this square brackets is the shift of chain complexes coming from the triangulated structure. And this tensor N is this N. It's tensor N times with this part of P1. Yeah, so these morphism groups, you get Chow groups, and if you put 0 and 0 and X and Y are projective, then you get 0 here and D here, which is the Hom groups from Chow motives. So in this way, you see that Chow motives fully faithfully embed inside this bigger category of Voevodsky motives. And there's also, so this is effective here, and there's also non-effective versions. If you invert this, if you allow negative N here, if you formally tensor invert that object. So an example of a realization functor that I'm going to focus on right now is de Rham Cormology. So now we're working with a triangulated category. So the target is not vector spaces anymore, but derived category of vector spaces. Okay, so this is a typo from when I was going to do étale Cormology. So this is the derived category of Q vector spaces. So if we have a smooth variety, we can take the étale hypercohomology of its de Rham algebraic de Rham complex, and this functor will factor through this category here, which is not even the way so with this definition, it's not even that difficult to show. So, I mean, by definition, these things will satisfy étale descent. And I mean, you know that de Rham cohomology is A1 invariant. So, I mean, just by the setup, so by the universal property, you get this factorization automatically. Okay, so now the modulus part. So let's look a bit more closely at this omega. So a special case is if we consider the affine line with the origin removed. So as a scheme, this is the spectrum of this ring here. So this it comes equipped with a canonical filtration. So here we have, this is this ring here, but we can also consider the coordinate ring of the affine line. And to get from here to here, so these are Qt submodules. Submodules. Or actually more generally, this two-term complex is it's a differential graded module over this DGA. And if we, as we consider all the n, we end up with this thing here. And so this extra structure can be used to study this, and it will also come up in other guises. And more generally, so here I used u instead of x because I'm going to use x here. More generally, if we have an open immersion and some effective Cartier divisor on x, who's such that u is the complement of the support of d, then we can take this pair xd, so which is our more grown-up version of this n. So we take this pair xd. So we also have between the algebraic de Rham complex of u and the algebraic de Rham complex of x, we have these intermediary differential graded modules over this CDGA. So this is the ideal. So this is the tensor inverse of the ideal of not of the effective Cartier divisor, but the divisor we get if we lower all the coefficients by 1. So if we remove, so here we used n minus 1. So if you have more branches on your divisor, then you want to put -1 on all of the coefficients. So yeah, we just tensor everything with this thing here, and then the rest of the complex is the log D algebraic de Rham. So this kind of thing appears in an article. It appears in various places, but in relation to this modulus story, it appears in a Ivora Yamazaki article about one motives, and there's this ruling Saito article on motivic conductors, where it also appears. So this is for the de Rham. And then, so this was with over Q, but if we're over P, then we can take this filtration on the O part and combine it with the Artin Schreier-Witt sequence, and then we get a sequence on the et al. Cohomology with mod PM coefficients. So we get these, we get these various objects which sit between the et al. Z PM cohomology of X and the PM cohomology of U. And there's also a cycles version where you put restrictions. So the Chow group of 0 cycles is the free abelian group of points of U modulo those ones coming from invertible functions on U. Not invertible functions, but meromorphic functions on U. So here I'm just, for the ease of exposition, I'm restricting just to smooth affine curves. So we can, if we put restrictions on which meromorphic functions we use, so here we have a meromorphic function. So this should be not O star U, but the meromorphic functions. So if we put some restriction coming from a divisor then we get larger groups which project onto this thing, and which sit in this sequence like this. So then the question is there a motivic theory which capture these intermediary objects? Okay, so here we have the slide from before. What is a motive with modulus? And so we can modify all of these answers. It's a filtered piece of a universal Cormology group, is one way of thinking about it. So it's a symbol where, so we have a more complicated, instead of a direct summand, we have a filtered piece, which is indexed by an effective Cartier divisor. Yeah, so this is, okay, well, I mean, this is not quite what I should have written U in here, I guess, but, or like instead of U pi, I should have written XD maybe. Anyway, we can still think of this constellation of filtered pieces of vector spaces, or we can think of it as a filtered piece of a homotopy type. And so this is the one that, yeah, I'm not going to say anything more about these ones. This is just to have a conceptual image. This is how I want you to think of a motive with modulus. Whatever picture you have of a motive, take a filtered piece of that. So here's the definition, which is a lot of text. What's on the next slide? Yeah, so you can read that in your own time. Or, I mean, let me put it up. If you want to read it now. But let me direct your attention down here. So here I've rewritten the the way I defined Voevodsky motives with rational coefficients before, which is actually dA. And so you take this definition and you add modulus everywhere. So you add modulus to the generators. So instead of smooth varieties in here, you take M smooth. So instead of a smooth variety, you take a pair. So down here, if you're over a field, your pair will consist of a variety equipped with an effective Cartier divisor whose interior is smooth. So the interior is the, where is it? It's the interior is the complement of the effective Cartier divisor. So these are our generators. And then we make a category out of these in some way, which I'm not going to describe now. We put a topology on there, which is very closely related to the étale topology. And then we take its derived category as we did before. And then instead of using the affine line, we use this pair, which is the projective line with the divisor, the point at infinity. So this cube, and I mean, it's not a cube, it's a line. There's historical reasons why it's called a cube, is P1 and the divisor. So here just put X bar equals the, X infinity is empty and X bar is the base field. And so you get P1 with the divisor, just the infinity. And you use this as a replacement for the affine line. And then you go back through all of the last 30 years of motivic literature and try and do everything with modulus. So the next slide is originally this slide was titled "Or But Why?" So I give you another chance to stop me, or I can do this slide for another 5 minutes. Okay. Okay, so there's various applications people have in mind. And one of them is class field theory. So if I take a smooth projective variety over a finite field, I can consider its, so this is the abelianization of the étale fundamental group of this smooth projective variety. And the zero means ignore the stuff coming from the base. So you'll have some automorphisms coming from FQ, that the absolute Galois group of FQ that you want to ignore. That's what this circle means. And it's yeah, so there's this Kato-Saito theorem from 1983, which says there's this cycle theoretic description of this étale fundamental group. So you can describe the elements of this étale group using cycles on X. And again, this little zero means ignore the, so you remove the part coming from the base. So there's always going to be a copy of Z in here coming from the base that you want to ignore. or yeah. And this group here, as we've seen in previous slides, is a morphism group in this category of motives. So then there's 17 years later, Schmidt and Speiser have a version of this, or generalization of this result. So where X doesn't have to be projective anymore. And so here you take still the abelianization of the étale fundamental group, but you look at the tame part. So you ignore the P torsion. And so, yeah, their version as a replacement for Chow groups, they have Suslin homology, which you can, if you want, take as definition this, it's the morphisms in category of motives towards, or this twiddle here is the same function as this zero. It means you ignore stuff from the base. You remove the part of MX that comes from M of the base. Okay, and then there's also variations of this result due to Schmidt, and there's two papers by Geisser Schmidt. Yeah, which disrupt the flow of my exposition, so I'm not going to, but I didn't want to leave them out of the slide. Okay, so this tame part, so you might ask, can we get rid of this tame restriction? So tame means that there's no ZP part, and ZP fits into this short exact sequence of étale sheaves involving GA, which is very closely related to the affine line, which we killed in DM. So we have this sequence, and these two objects we killed, which means we're also killing this one. So no, there's no hope in Voevodsky's theory. Like from the very foundational way it's defined, there's no hope at all of inside Voevodsky's theory of having a description of wild ramification, because we killed it as a basic starting principle. But nonetheless, so another almost 17 years later, there's this result by Kurt Saito. So they do have this cycle theoretic description of the abelianization of the étale fundamental group, including the ramified part, where they enlarge the Chow groups in the way that I very briefly covered here. To allow, yeah, so they made them a bit bigger, coming from in a way that's filtered by this divisor at infinity. And so there's a hope, there's a general hope in the community that if you use motives with modulus, then you can have this home group description that also includes wild ramification. And so, I mean, various other reasons why you might prefer this category to Voevodsky's category is K-theory is, so general K-theory is not A1 invariant. If you just work with smooth varieties, it's A1 invariant, but more generally, it's not. And so you might like to have this motivic cohomology to K-theory spectral sequence for not for homotopy invariant, not for A1 invariant K-theory, but for more general K-theory. Or if you like studying Jacobians using motives, there's more generalized Jacobians which have unipotent parts, which again, there's no way Voevodsky's theory the A1 invariant theory can see this because you killed all the A1 stuff from the beginning. All right, so so then there's, I explain what does my paper with Miyazaki add, and then that's the last slide.
So thank you very much. Thank you, Shane.
Thank you.